Also, super windy today, right? Okay, super windy today. Let's get the whiteboard up because I like using this whiteboard as opposed to other things because the pen happens to be prettier, and that's all that matters, right? Okay. So let's go ahead and let me pull up chat so I know if people are talking to me. Okay. Exam 1, right? So it is open book, open note, open all the kinds of stuff you want to open all the kinds of things. Remember, right? If you find something on the internet and you're going to use it, even if it's part of an answer or something, you need to cite it. Right? Worst case scenario, if you cite something, is that I might go, yeah, but I wanted you to do it yourself. Do it again. If you cite it, it's never going to be plagiarism if you cite it, because by definition, you have not claimed that work as your own. You have said, I have found this. This is somebody else's. This is the relevant answer to the question, which is a useful answer in itself. Please cite everything. Citing is, you can't get in trouble for citing, but you can definitely get into trouble by not citing something. Okay. I mentioned this because it for my freshman student, it did bite them in the tuchus, last semester on their final, where they found something and they did not cite it, and it was also wrong. So, all right. So, okay, just to be clear, we will have a question like this on the exam tomorrow, okay? So for each of the following questions, indicate the data structure that would be best suited to handle each scenario. Your choices are the following. To make it easier for me to grade, they're just simply multiple choice on the exam. So you'll be given 4 options. Please select the one that best represents it. Okay. So you need to model which patient should be seen at a hospital. Ooh, this was a cogent question. This was an uncomfortably relevant question the last couple semesters. Patients should be seen in as close to order of arrival, but patients in a more severe situation should be seen first, right? This is the triage kind of model that hospitals use. If you've got a broken arm, having somebody who's got a concussion takes precedence over you, even if the concussed person arrived after you, because your arm being broken, that sucks. But you're not going to die from it, whereas a concussion could be potentially fatal. All right, next. So which model? So which data structure organizes this best? Right, a priority queue or a heap. A heap, and Stephen, you use a heap to build a priority queue. So you aren't wrong, right? It's just not one of the options that I put up there. So priority queue. It is a queue, but people can cut in line. That is a priority queue. All right, now a router needs to hold packets in a buffer and deal with them in the order they appear, right? This is the way that routers work, right? That is a queue, right? The idea here is that routers, they take in things, right? They take in data and they try to sift out to where it's going to go, right? They take incoming data and they send it to the appropriate computers and devices. Some stuff will go to your phone, some stuff goes to your laptop, some stuff goes to your parents' laptop, some stuff goes to your roommate's laptop, whatever. Don't know why you have a roommate in your parents' house. I don't know. Okay, so that's a terrible joke. All right. Although, okay, so 3, you need to model a hierarchy. Any kind of hierarchy, yep, any kind of hierarchy is a tree. That is kind of what trees are used for. If you're not using them for sorting data, then it's used for hierarchical stuff. That thing with leaves, right? As I've mentioned in many videos, computer scientists don't get outside too much, so it's a tree, T-R-E-E. It is the thing with green leaves, right? You may have heard of them and may have even seen them. They're the things that release pollen and make your allergies awful. Okay, you need a data structure to hold your previous decisions in case you need to backtrack. Pancakes. Right, stack. Okay, so the wrong answer to write here, which you cannot write because, so the wrong answer to write here is recursion, because recursion is not a data structure. You want a stack. And nobody sent me recursion in private messages. I'm just saying that is an answer that I've seen on final exams when I give this. There will be a question like this on this exam and on the final exam. Okay, I can't have pancakes right now because it's Passover. So, you know. All right, so tree vocabulary questions. On the exam, it will be very similar to the quizzes that I've put that you have. So answer the following vocabulary questions. So what is the node at the top of the tree is, what do we call that thing other than the node at the top of the tree? The root, right? So you've got links from a node to its successors. What are those links called? Edges, branches, and links. Because of course, if I put this word in here, that describes it, you know. So yeah. Edges and branches and links. Yes, those are all appropriate answers. So the predecessor of a node in a tree is called what? What do we call that? A parent. Yeah, we call that parent. We also can call that the ancestor or the predecessor. If you are nodes that have the same parent, then what are you? You are siblings. That is correct. So now let's describe, without using code, how would you calculate the height of a tree recursively? Anyone want to take this? You can open up, you can unmute yourself if you want to. Or just say no. Okay, so how do you figure out what the height of the tree is recursively? Well, let's take a look at it from the perspective of just of Mr. Root over here, right? So the root of a subtree. Okay, so let's just say I'm here. I'm just the happy root of a tree or a subtree, right? So, and I have a left subtree and a right subtree. I have some number of nodes to the left, and I have some other nodes to the right. Yeah, you kind of keep going down until you have more kids, but you gotta figure out. So first off, I need to establish a base case. My base case is actually more to the point of if this is me, Mr. Null, right? What's the case if I'm null? Hadassah's got it, right? So what is the base case over here?
Height is 0.
Height is 0, right? If I'm empty, then my height is 0. Okay. Otherwise, it's going to be some case like this, where these triangles represent a subtree of unknown size. It could be 1. It could be their heights could be 1. Their heights could be 1,000,000. It could be 0. But yeah, what you're going to do is simply say, okay, if I exist, I'm just going to give back 1 for my height plus the max of the heights of left and right. Right, so recursively call those. Right, so you figure out, okay, my height is 1, and so my answer is going to be 1 plus whatever's bigger, my left or right. Okay, not too hard to do that. All right, so let's draw an example of each of the following binary trees using a different example for each possible tree. Now, the reason I tell you to use a different example is because I could draw this guy and he is perfect, full, and complete, because of course he is. That cheeky guy. So, right, so a perfect tree, if you've got a height of h, then a perfect tree will have n to the h minus 1 nodes in it. Sorry, we'll have, h 2 to the h minus 1. Yeah, look at me tumbling over my words. 2 to the h minus 1 nodes in it. So perfect, and that's graphically, that means the tree is always going to look like one of those mathematically ideal units, right? So this is a perfect tree. Perfect trees are also full and complete because they are full because they have all the nodes either have 2 children or they're leaves, in which case they have no children. And then the bottom, and then it's complete because it's perfect up here. And then it is filled in left to right. All right, so an example of a full tree could be this guy, or we could do not that guy, he ain't full, but this guy, or this guy, or this guy. This is a full tree. Definitely not perfect and definitely not complete, certainly not balanced, right? But look at this guy, right? Every node has either 0 or 2 children. Okay. So, insert joke about parents bugging you about when you're finally going to get settled down and have kids. So anyway, and now a complete tree. Complete trees are awesome. We typically use them for heaps, right? And this is an example of a complete tree where the top layer is perfect, and this layer is going to be filled in left to right. So if I do this, this is no longer a complete tree, right? We've got a gap right here, okay, which is no bueno. Okay, this is perfect and complete, but let's go ahead and ooh, that's cool that I can do that. But let's go ahead and just kind of demonstrate some more. This is complete, not complete, because this guy had a right tree that I need to be filled in. So this is a good example of a complete tree. Okay, so another example, another kind of question I love to ask is, you know, what nodes need, so let's go ahead and say, I've got this situation, you know, I've got node and I've got sorry, let me go ahead and write it outside here, A, B, C, D, which guy needs to be removed to make this a complete tree? And the answer is D. George, I'll let you know when I figure that one out. How'd you tell if it's complete recursively? You can't really. Not everything with trees can be done recursively. Not every problem can be solved recursively because complete is not a recursive property. It is a kind of, what complete is that it's an array translation property. So what we do is that we can, with complete trees over here, is that we see that we've got I said type. I said I want, you know, there we go. I don't know why it doesn't. So A, B, C, D, E, F, G, right? When we care about completeness, and then H over here, we care about basically, does it map into this array without any gaps? Basically, A, B, C, D, E, F, G, H. 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. So basically, does it fit into the indices? Basically, can we fit this? Rather than fitting this as a link structure, could we encode this as a array space structure without any gaps? That's kind of what we're asking for a complete tree, which is why we use it for heaps so much.
How would you go through and make the tree? Would that just be, if you're gonna do A, B, C?
This was a breadth first search that I just went through. That was breadth first search. So A, then B and C, then D, E, and then F, G, and then H. Breadth first search. So which we'll learn about in graphs. Although you probably learned about it already. All right. So in this one, typically what I'll do, I think on the exam, it's more along the lines of I'll give you a tree and ask you what wouldn't have built this tree. What would not have built it. So let's go ahead and yoop. Okay, so basically we want to insert the following node. We want to build the following tree out of everything. So let's go ahead and move over here. So our root is gonna be 42. So then 10 goes to the left of that. And then 50 goes to the right of that. and then 12. So 12 goes to the left, then to the right. So 12 goes over here. Then 17 goes to the is less than 42, but it's greater than everything else. So it goes over here. Really, why is just not wanting to do that? 17. Okay. 80 is greater than everything on the tree. So it goes all the way to the right. 80, I said not 18. My hands don't always listen to what I want to say. Negative 12 is less than everything. So it's going to go all the way to the left. 100 is bigger than everything. So it goes all the way to the right. 96 is not bigger than everything. So bigger, 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 smaller than this. Then 105 is bigger than everything. So we're just going to go ahead and add a 105 over here. 86 is going to be 80, less than. So 86 over here. And then 72. Did I add everything? 42, 10, 50, 12, 17, 80, negative 12, 100. 96, 105, 86, 72. So 72 less than. So 72 would go over here because it is less than 80. Right, so your tree probably should look like this, unless I messed up somewhere, which is entirely possible. So using the previous answer, draw what happens when you remove the following. And again, it will be a lot like the quiz that you got, which is like, here's a question. Show me what happens when you remove something. Okay, so 42, 12, 17, and 62. So 42, right? We've got 3 cases for deleting a node. No children. 1 child. 2 child. And 1 child, no children and 2 children are easy. 2 children is hard. So 2 children. What do we do? So 42 has 2 children because it's the root. So what do? We need to find the next in order predecessor to become the new root of this subtree, which happens to be the tree itself. So what we're going to do is that we are going to take 17 because so how do we find the next in order predecessor? The smallest thing that is the biggest the biggest thing that is smaller than what we currently have. Well, my left subtree has all the things that are smaller than me. And to find the biggest, we go all the way to the right. So that's going to be 17. So we need to replace 42 with 17. Now to remove this node over here, it's just a single child, so just kind of delete it. And this
Yeah, I
is
thought it was the other way around. Is it either? Like, do both work?
oh yeah, totally. Both work. You can find the next in order successor by going right and all the way to the left.
Okay.
Either of those will work so long as you're consistent throughout your answers. I like to do the next in order predecessor. Okay, so next what we can do is that we need to delete 12. 12 has no children, so we just simply tell its parent, 10, hey, replace me with null. And the parent obliges. No, I don't want a ruler. I want an eraser. All right, next. 17, delete 17. Just got here, but it's got 2 children. So we go 1 to the left and all the way to the right, which happens to be 10. Okay. So we go ahead and I'm going to show you, right? So what we do is that technically the way I describe it in code is I say we replace this with 10. We replace this with 10, and then we ask the tree to delete this node over here. So how do we delete this node over here? Well, it's got 1 child. And what you do when you have 1 child is just you simply tell your parent to adopt your child. Which is fairly straightforward because all I have to do that is draw this line. Okay. Now, Next, when we delete 96, again, we find 96 over here. And again, it's the same kind of situation. It's just a matter of telling your parent to adopt your child. Okay. And so that's how, yes.
So my root is 50. Is that okay or no?
If your root is 50, that's because you did your in order successor, and that's perfectly fine. For
Okay.
the multiple choice, I think I'm going to be doing next in order predecessor. But again, you're going to be selecting like which of the following nodes is what you get after you delete. And
Okay.
all the other ones will have a mistake.
Okay.
All right. So let's go on. Let's continue. Which of the following is the pre-order traversal of a binary tree with these two subtrees? Do the left, root, right. Well, what is that one? Is that pre-order? What is this order? That's in order, right? So it can't be pre-order. Pre-order would be this guy, which is root node, then the left node, and the right node. This is when you handle yourself last, which is do left, right, and then yourself last. That's post order. And this is just plain wrong, I guess, number D, but I had to come up with something. All right, heaps. Draw the min heap that forms after inserting the following integers. Okay, so our integers are 8, 10. So here, so we need to do a min heap. Remember, and so for min heap, I like min heaps because describing min heaps because the way it works, they're min heaps until we get to heap sort, in which case we do max heaps, which is annoying. But I will describe, I'll tell you whether it's a min heap or a max heap. So regardless of whether it's a min heap or a max heap, by the way, they have the same runtime. So, all right. So first thing we need to do is enter 8, right? And then what we're going to do is that, remember, the heavier items sink to the bottom and the lighter items bubble up to the top. So what we do is that we always insert our items into the next position that would keep this tree complete. So that would go over here, right? And that's because what's actually going on is that we're inserting these guys into an array, 8, 10, and then we'd put in 50. And then we'd put in 20. And at that point, we'd have to rearrange things. But so what I'm actually doing over here, what I'm drawing, which is what I'm looking for in the answers, that's just giving me a nice representation of this. Okay, so 8, 10, 50. And once again, once you submit your exam, some stuff will be auto-graded. So you might look and go, I got a 60 on this exam, and just double check. It's probably that the coding questions haven't been graded or something like that. So 8, 10, 50. Now we do 20. Now 20 is heavier than everything else, so it's perfectly fine. So now we put down a 1. Now 1 is lighter than its parent over here, right? So we need to start swapping that around. So what we do is that we say, hey, if I'm lighter than my parent, I'm going to bubble up.
So I had a quick question.
Mhm.
Do we have to show each step
No.
during the exam?
Just no, I'm pretty sure that I'm pretty sure no. You
Okay.
wouldn't have to show each step. What I care about is that last answer. But if you want to show your work, that's always good. That's always preferable because I can always get partial credit. But there should be a way to upload that, or you can always email it to me. Now, anyway, the next thing we do is that we had 1 and 8. So again, those will swap because 1 is lighter than 8. So 8 will sink down over here. And then 1 gets to the top. It can't bubble up any further. So next is we insert 4 over here because it is the next space for things to be complete. 4 is lighter than 50. So we are going to swap those two. And I'm going to take the moment to redraw. So 4 is lighter than 50. And 50, and then 4 is heavier than 1, so it's not going to bubble up any further. Finally, we have 3 over here. So what are we going to do? We swap 4 and 3. 3 is lighter than 4, so 3 bubbles up over here. And also notice that each heap is a each sub heap or sub tree of this is also a min heap, right? So this is a min heap. This is a min heap. And the whole thing is a min heap. All right. So most people can get through the min heap adding, but it's the min heap removing that some people have difficulty with.
Does it
So
matter, like at the bottom, like with the leaves, does it matter like if the 10 and the 20 are flip-flopped?
it does actually, I think, because
Okay.
of the order in which you do stuff. So
Okay.
because what you're going to be doing is you do 8, you do 1, 8, 50, and then you do 20 there, and the 20 stays still. And then once you put in the 1, that's when things flip.
Okay.
So it does matter. Because the order in which you insert stuff does like kind of flip stuff around. So now what we need to do is draw the heap after removing an element twice. So right now, all we know how to do is remove elements from the one place, and that is the root. So to do that, what we do is that we delete the root, right? Because we use the min heap to always have the minimum element at top. And then what we do is that we take the last guy from the complete, we take the guy at the back, the guy that if we remove him, the thing would stay complete, and we put him over here on top as the root. Now, obviously, right, is this a min heap anymore? No. So we need to reheapify, but we've just moved this item. So what we can do is that we can basically have him sync to the appropriate place. So 4, we check him against his children, which is 8 and 3. 4 is lighter than 8, but heavier than 3. So 4 should swing down. It should sink down. I said swink. I don't even know what that is. So 4 should sink down and 3 should bubble up, assuming I can draw. Okay. And then 4 can't sink down any further because he's got 50 and that's heavier. So the next thing we want to do is delete the next item, which is 3. Notice that we've just deleted 1, then we've deleted 3, which were the 2 smallest items in here. We will be replacing 3 with 50 because that was the next item over here. So because this position was the next item to remove, the backmost item in a complete tree. Removing this would keep the tree complete. So, and now 50 has 2 children, right? So 50 is here. It's no longer a complete tree. So it's no longer a min heap. So 50 looks at his children. He goes, hey, I've got 8 and I've got 4. I'm heavier than both, but I'm going to swap with my lighter child since the lightest thing should always bubble to the top. So it's going to swap with 4. So 50 will swap with 4. I really have no idea what I'm doing here to make it hate me so much. Okay, and 50 can't sink anymore because we hit bedrock. Okay, we can skip the Huffman coding because I don't want to try to teach that, because you already have enough stuff to be getting on with in the semester where we're still all socially isolated with COVID. And really, that's what I think makes this semester so difficult. It's not necessarily the nature of learning online. Learning online, as long as you've got professors who know how to use the technology, is perfectly acceptable. It's the complete and total isolation from everybody else that makes it really difficult. So let's go ahead and do this method. Now to get into the coding, which of course is the part you guys care about because they're worth oodles of points and, they're the parts they ask you in interviews. So write a method which, given the root of a tree or subtree, computes and returns the number of nodes in that tree or subtree. May not use the size method, So I'm not going to basically create the tree. What I'm going to do is that I'm going to, again, I'm just going to create a new class here, exam review. And what am I going to do? I'm just simply going to create that method over here. And I'm going to create a private static class in there. So private static class node. Okay. Node E. All right. So I'm just going to create that class over here just so that I can simply use it, because that's all I need for the methods. Testing it will be a bit difficult, but honestly, I'm not really testing these things. And when I'm writing an exam, I'm just trying because I could have compilation errors at the wazoo. First, let me quash an error by returning -1 over here, because I always make it so my code will always be compiling. So, and then the node for trees, right? They have two things we care about. We have a left side, we have a right side. And well, sorry, the third thing is, of course, the E item or E data. I'm just going to call it item here. It doesn't matter what you call it. Okay. And then we need a constructor, a relevant constructor. So public node takes in, and that will take in an E item. And we're just simply going to say, hey, this object's item is going to be equal to the item that you just plopped in here. Great. Okay. Now view, let's go ahead and do, let's see, view. Appearance should be, let's go presentation mode. That did not, settings. Just wanted to be a bit bigger. Presentation mode size. 36. Apply. And then editor, font. I really like having a large font size on a large computer because it's just much nicer for everybody. So view, appearance, exit presentation mode, view, appearance, enter presentation mode. There we go. And view, appearance, enter distraction-free mode. There we go. Nice and minimalistic. Okay. So hopefully you just learned something. So you can really not make this thing a minimalistic kind of powerful editor. So we want to figure out what the size of the tree is without using the size method, right? So forget that it even exists. We need to count the number of nodes in the tree. So let's figure out my base cases. My base case is pretty easy, which is that, hey, if I always ask the question, hey, if I don't exist, what's the end? What information does that give me? So if the root is equal to nothing, sorry, not root is equal to null. What did I do? I'm just getting ahead of myself and combining what I'm trying to type. So if the root is equal to nothing, if the root doesn't exist, how big is the tree? Not big at all. It's got a size of 0. So otherwise, what is the size of the tree? Well, we've got, well, then I'm in that case where basically I have, so again, if I am just trying to figure out how big I am, then I am kind of in this case that we saw in this class, which is that if I'm not null, then there's me, and then there's my left tree and right tree. So, well, I know how big I am. Int me is equal to 1. I am 1. Then I've got my left subtree and my right subtree. So int left size is equal to whatever the size of the left subtree is, right? So I'll ask my left subtree to figure that out, because that's a tough question. I don't know how big he is. And same, he might not even exist. But if that's the case, then he'll tell me null. We have this null check over there. Right size is equal to size tree root dot right. Okay. So I've got my left, got my right. So I can just simply add that all together. Return. So the total size of this subtree would be the left size plus me plus the right size. There we go. 1 second. I think I hear a dog. So. Happy feet. Come on. Happy, come on. Here. Oh, yes. Hi. One of the benefits of working from home is pets and not having to worry about students' allergies. All right. So we can, of course, make this, we can totally like streamline this down into this else clause into like one line if we wanted to. We could just simply say, 1 plus size tree left plus size tree right. Me is just simply the size of the root. So I could just simply easily eliminate that. I was just kind of jotting down my information as I was writing it. Okay, I was trying to make it, nice and able to follow my thought process. Incidentally, the amount of time this takes is O of n time because we are hitting every single node in the tree. So let's go ahead and write a method which, given a tree, returns whether it's a full tree or not. So it's very different. So it's different because it's not like, it's not like a zigzag method or a get everything method. It's the cases are a bit weird, right? So you need to consider like some things like, if root is equal to null, let me go ahead and switch this from tree to root. So if root is null, I don't know whether I'll just return true. I guess if I don't exist, then then all the nodes either have 0 or 2. Then all the nodes have 0 children, right? If I don't exist, I guess I'll return true here. I guess that's my base case. Otherwise, right? Well, let's think about kind of the base cases, right? Because we can actually draw a bit more information than we normally do. Right? If I don't exist, we've got this weird answer, but otherwise, right? What can I say? If it's just me, then I am definitely full. If on the other hand, I have a left child, if I have a left subtree, but no right subtree, or a right subtree, but no left subtree, that is totally, really? What's going on here? Not full. Make sense? Right? So, right, if I don't have any kids, right? If basically this is a blank, if this is a null, and this is also a null, right? Then I'm full. If both my kids are null, then I am full. Right? So if root dot left equals null and root dot right equals null. Here, do you move that down for you? Okay. If root dot left is equal to null and root dot right is equal to null, then this subtree is full. I'm going to return true because I don't have any children. So I have 0 children. So I'm a full subtree. Okay. Else if, and we'll just simply copy paste this for expedience. If root.left is not equal to null, so we have something there, but root.right is null. So we have a left child, but not a right. In other words, we have one child. But if we have one child, that's not 2 or 0, so return false. Otherwise, and then we also have the the opposite case where my left slot is blank, but my right slot is full. And that's going to bug me. So there we go. And so we'll also return false there. Make sense? So we kind of got 3 of the 4 combinations, right? A and B are null. Sorry, left and right are null. Left isn't null. Right isn't null. And now there's one more case, which is left and right aren't null. So otherwise, else, otherwise both are occupied, right? Oh no. Well, what do we do? Well, I can't just return true. Because while I'm full, I have 2 children. I don't know, do the nodes in this subtree have 2 or 0 children? What about this subtree? Right? We don't know that. We don't. So what we're going to have to do is basically ask that. So return is full root dot right and is full root dot left. So I'll be able to say this subtree is full if my left subtree and my right subtree are full. Although I should technically do it left and right because that's the proper order of doing things. And I don't know why I did it the other way around. So that's how you do the is full. Does that make sense? Time. Good timing. Okay. Next one. Let's see. What is our next problem? Ah, yes, the extra practice problem, which I love doing. We haven't learned breadth first search, so to speak. We're just doing the recursive methods, so just depth first search methods, kind of. Okay, so static Boolean equals. So here we're asking tree A and tree B. We're asking if these 2 trees or subtrees are equal. And the way we do that is we ask, hey, do they not only have the same data, but do they have the same structure? Do the left subtree and the right subtrees, do those also look the same? Does this zig when, does it zig when the other one zigs or not? So, okay. Let's go ahead and plop this in. So, okay. Why is it giving me cannot resolve symbol E?
The E isn't in the name.
Oh,
Doesn't
yeah,
have to
yeah, yeah.
equal the static E Boolean.
Ah, yes, I have a typo there. Thank you. Good catch. Okay. Man, suddenly I'm all sorts of tired. Don't know why. Probably all that wind blowing. Okay. So first off, we've got root A and root B. So first off, base case. If really what we care about first off is are they both, well, let's go. Well, we can't just simply say conclude anything if A is null. And we can't conclude if anything is if B is null, like we normally do. Instead, we have to ask ourselves what combination of null are they, right? So if tree A equals null and tree B is null as well, then that seems like a pretty good base case to start with. If they're both null, right? Then what's going on? Then I'd say they're equal, right? They don't exist, then that seems equal to me. So return true. So actually we can then kind of use something similar to what we did above there, which is else if tree A, let's go ahead and grab this again because we're going to be repeating this quite a bit. Else if tree A exists, but tree B doesn't, right? If something exists, if one thing has a value and the other thing has like the opposite of having any value, then return false. Insert joke about industry of your choice not having any value. Okay, so oh, and of course, what I need is the actual words to make this work, which are else if. Right. So if one thing exists, but the other has no value, it doesn't exist, then they can't be equal, right? So these are some pretty good base cases, right? Where we don't really have to do any work and don't have to do any anything else recursive, right? So now, otherwise, they both exist, which is a bummer because that doesn't make it easy. So now that they both exist, we can actually like say, hey, maybe we should check the values inside of them. And we can do that because we know that neither of them at this point are null. So if tree A dot item dot equals tree B dot item, and let's go ahead and actually turn that into a not, because that actually becomes another easy base case, right? So if they exist, but their items don't work, if their items say, hey, if their items basically don't match, right? If the data inside them doesn't match, then they can't be equal, right? It's got to have the same values and they've got to be in the same way. So return false. So if their items don't equal, we can return false. Otherwise, we just found out that their items do in fact equal each other, which means that now we have to check their subtrees. So what we have to do is simply, so at that point, what we have to do is return, hey, equals tree A dot left, tree B dot left. Are the left subtrees equal? And are the right subtrees equal? Because if the left subtree are equal and the right subtree are equal and our values are equal, then we can just simply say, hey, the whole thing is equal.
Professor.
Yes.
So I kind of just, like in the else part, I just wrote one big return tree A dot item equals tree B dot item and equals tree A dot left, tree B dot left, and equals tree A
That's
dot.
fine.
So if it would say that tree A dot item dot equals tree B dot item, like if that becomes false, will it
Yeah.
continue checking the equals?
No, did you write it with double ands?
Yeah.
If you've got double ands, then it will short circuit. So that means that, so basically what that means is that, right, if we get to here, okay, if we get to this line over here and we go tree A dot left and tree B dot left and we get a false over here, it's not going to bother continuing on to this because it would know that if one thing is false, then the other thing isn't worth checking, right?
Yeah. All right, that makes sense. Thank
Now,
you.
this is also why you want to avoid using kind of any kind of I++ stuff in a statement like this, like because if you had an if statement, by the way, if A is less than 7, and I is greater than or equal to 15, right? And this statement was false over here. This would never run, which means that your I++, which you might be counting on for some reason, which would increment, to increment that would never actually increment. So it's part of the reason why we just don't like to use inline I++s at all. That's just kind of an aside there. It's one of those things that is a holdover from C. I'm not sure if you can still do it in Java, but don't. You shouldn't, just because you can doesn't mean you should. All right. Okay, now we're into the map portion, which is write a method which returns what characters occur in a string and how many times each occurs. It's fairly straightforward. Okay. What characters occur in a string and how often they occur. So we know what kind of map. We know that we need a map of this type. We're going to call it the map, and we're going to say it's equal to a new hash map, which will automatically get imported, and we will return that map at the end of this statement. Right? We're counting how often each of the characters occur. Technically, you could do this with an array, with setting with an array of a certain size and set the ASCII value or the UTF-8 value to the index, but then you're just making a map, but making it harder for yourself. So might as well just use the actual map. So for car letter in word.toCharacter array. So for every letter in the word, what are we going to do? We are going to first ask, hey, if map dot contains key letter, if not contains key. So if we've not seen this letter before, what are we going to do? We are going to add it to the map. Map.put letter, and hey, I've seen it once now. Great. Otherwise, I have seen it before. So let's go ahead and get int sightings equal to map.get letter. So I'm going to get how many times I saw it before, and then do map.put letter int. So sightings +1. You want to say hi, Laser? You can come up. All right. So we can also reduce this, by the way, by making this a bit messier. By just simply, we can make this a bit messier by like putting this in here. By the way, the code is done. Very short code. There's also other things you could do, like I think there's a map dot get default. Get or default. So this one's actually pretty cool. So let's see how that works with this case. Get or default is one of those really cool methods that just, you know, I don't go over because it's not, because I don't want to overload you with information. And it's unnecessary, but it's one of those nice shortcuts. So what we can do here is do map. We can do int sightings. So how many times have I seen this letter? Is equal to map get or default. What in the world does this do? Well, what it will do is say, hey, if I've seen this value, get it. But if I was going to get a key error because this doesn't exist, right? If letter hasn't been seen yet, if it's not in the map, then give me a 0. So if it's in the map, give me the value associated with letter. If it's not there, give me a 0. Make sense to everybody? Okay. And then what I can just do now that I've gotten the number of times I've seen that letter, which is either the previous number of times I've seen it or 0, I just simply say map.put letter and sightings +1. Okay. And again, I can just simply reduce that by just slapping this in place of sightings to make it smaller. But that, would be a bit tricky. Okay, I'm going to skip question 20 for now because that's a categorization question and that's not on the exam. So I'm instead going to skip over to the analysis just to make sure that we have time to talk about everything. So what are collisions in hash tables? Why do they occur? Oh boy. And how are they handled? Okay. And let me go ahead and actually, I'll grab one more. I'll grab you guys one. I'll do you I think the parlance is a solid, and grab one more question from the actual exam for analysis so we can go over it, because I know if you see something like, oh no, I have to analyze something, it will be super duper scary. So.
How many analysis questions will there be?
1, because I like my online exams to be shorter than paper exams. Okay. What are analysis? So what are collisions in hash table? Why do they occur and how are they handled? Any takers for this? Or do you know better than, or do you know by now it's better than to volunteer information like that?
Isn't it when an entry has,
Go ahead.
isn't it when an entry has the same hash code?
Yeah. So when an entry basically has the same hash code as something else in a hash table, that's a collision. And when they basically try to occupy the same index, right? Now, why does that happen? This is one of those not a trick questions where it has a fairly inane answer for it. So why do collisions happen? I've got somebody in chat saying something. Right, not infinite array. Right. So the idea here is you've got more possible things you might want to put into a hash table than the hash table could possibly hold. Or you've got the size of keys are infinite, but your table isn't. So, it's possible that you can select things that have this, that end up having the same location. So when you do get a collision, what are strategies to get around that? How can you handle that? All right, so we learned about 2 in class, 2 broad strategies. So one is, yep. So Stephen, linear probing, well, technically is correct, is a strategy. It is a type of what we call open addressing. And the other one we learned in class is chaining. So open addressing simply so what is open addressing? That simply says I'm going to look for the next possible spot in the hash table. And chaining says that actually, well, collisions aren't a problem because this town is big enough for the both of us, right? What it is that in chaining, what you do is that every single index instead has a linked list. So you just simply add it into the linked list. It's also called bucketing. So Harrison, yes, but that helps prevent collisions. But what we are talking about is more what happens when we get a collision. There are multiple ways of handling collisions, by the way. So again, open addressing simply says, what is the next? If I can't fit in this space, I'm going to look for the next available space. So now what is next? That depends what kind of probing technique you're going to use. With linear probing, next available space literally means next available space. if I want to go to I, I'm going to check I plus 1, then I plus 2, then I plus 3, then I plus 4, and so on and so forth until I find an empty spot. And there's guaranteed to be an empty spot because we're going to keep resizing when there's not enough spots left. The issue is that this can create clumps in your hash table. But okay, next. What about we can also use something called quadratic probing, where the next available space is defined like this. If I can't fit at I, I'm going to check at I plus 1. If I can't go there, I'm going to try I plus 4, then I plus 9, then I plus 16. In other words, instead of doing I plus 1, I plus 2, I plus 3, I'm doing I plus 1 squared, I plus 2 squared, I plus 3 squared, I plus 4 squared, and so on and so forth. The advantage of this is that it's less clumped, is that your hash table is less clumped, but you now, for those people who are really optimizing their hash tables and stuff, you kind of get mildly annoyed that you've got a multiplication operation now in addition to an addition operation. Okay. And then, so you've got a much more complex operation added in addition to the plus operation you were doing. And then also, you could get really unlucky with just, it could take a long time to find that, but. Okay, now with bucketing, you just simply throw it into a linked list, and if the linked lists, and hopefully the linked list will be balanced. There are other ways to do it, like I believe cuckoo hashing, which is kind of it's kind of funny. It's a resolving hash collisions in hash function table with the worst case lookup time. The name derives from the behavior of some species of cuckoo birds, where the cuckoo chick pushes the other eggs or youngs out of the nest when it hatches. The idea here is that when you put a new key into a hash table, you basically say, that's my spot, get out, and kick that other key to a new location. So clumping's bad just because you would have to check more locations for that, and it wouldn't be as evenly distributed as possible. This also brings into other things, like you have double hashing, where basically if one hash function doesn't work to find a spot, if the hash function says your spot is already taken, use this other hash function to find a backup spot for you. So which could lead to collisions in and of itself, but that's a problem. But so there's different ways to do it. But by far the academic techniques that are most studied are the ones we just covered here. What are the worst case runtimes of insertion and deletion algorithms in binary search trees, and why? So what is the worst case runtime for insertion and deletion in a binary search tree?
O of n.
Right. It's O of n time. Why?
Because if it's not balanced, then it's basically just like a list.
Yep. If it's not balanced, it's basically just like a linked list. So we can get a binary. So right, a balanced binary tree is nice because everything is basically within a factor of basically the no branch is more than one bigger than any other. So, but if it's unbalanced, right, we could get something like, well, we could get something silly like this, where it's just simply a diagonal linked list. But we could also get something like this. And this is totally unbalanced still. Right. And the idea here is that, right, in a balanced binary search tree, right, the idea here is that your left subtree and your right subtree, those guys are about the same size. Okay, these guys are about the same size because and so what that means is that if I'm looking for an item, if I decide it's on the left side, then I don't have to search that right side at all, right? And that's basically reduced my search space in half. That's why we get our log n time, because every time we make a move, every time we check something, we are removing half the items from our search space. That's how this works. That's why it's log n. It means every step we take is going to reduce this by half. Meanwhile, though, would be O of n, because if we're looking for an item, every time I make a move, I am only really ever reducing the search space by 1. Okay, so that's why the runtime for insertion deletion algorithms and binary search tree are O of n. Now, to rectify this, all right, let's go ahead and talk about rectifying this. Okay, which is that you use a balanced binary search tree. And the way it is that you assume your tree is balanced, right? We assume that this tree is balanced, okay? Now, if I'm adding something to a balanced binary tree, okay, it takes log n time, worst case, if it's balanced, right? But suppose I add something and it makes it unbalanced, right? Well, fortunately, it turns out that it takes only log of n time to rebalance a tree. If basically just putting in this, if it was balanced before and now me touching it has made it unbalanced, either by adding or removing, then it takes only log n time to rectify that mistake. So overall, we'd have a log n operation and another log n operation for a grand total of log n, big O of log n. So binary, so that's pretty good. So let me go ahead and pull up this exam from this is the actual exam and the actual question I've asked on that exam, which I probably won't be able to ask anymore because I'm recording this session. Should have thought of that, Andrew. You did, don't care. Okay, so we like to say that that data structures built using hash tables can do constant time operations. Give a scenario where inserting or deleting an item from a hash table might take O of n time. So what's kind of a scenario that could happen? Where adding something, adding or removing something from a hash table could take O of n time. When a collision occurs, well, I mean, like not always. Like specifically when a collision occurs and what else? Well, yeah, you have to do linear probing, but okay, the next spot's open. That still took constant time. The location of sorting is I plus n. I think you might be thinking a bit too deeply on this one. Don't overthink this one. Right? If you, yep, Thomas has got it. If there's only, if basically if you aren't expanding your tree, if you aren't expanding it properly, right? That way you'd have to probe the entire hash table. Yes, if you have to go through and probe every single thing, if there's only one open spot left, then yeah, it's going to take O of n. A similar thing when you're using chaining is if everything simply maps the same spot, then it will take O of n time. That also applies to open addressing, by the way. If everything maps to the same spot, then insertion and deletion is going to be O of n time as well. So, so one answer might be if my hash function is, so let's go through that. One possible answer is if my hash function is terrible and it is, if my hash function is h of x, where x is my key, is equal to 2. That's a pretty terrible hash function. That just maps everything to index 2, essentially. So that won't work too well. Because everything you do now is going to do a collision and it's going to take O of n time, where n's already the stuff already in the hash table. Similarly, if we haven't been rehashing and readdressing this, right? So if our table is completely full, except for this, except for this spot over here in the middle. And we hash over here, it takes approximately O of n time to find that empty spot. So yeah. So there are a lot of reasons why that might occur.
But a hash function of how you designed it in the videos wouldn't, because it's a good hash function and you rehash it, nothing would really hit O of n time.
We assume that the hash functions I'm giving you are pretty good unless otherwise stated. because again, hashing is black magic with prime numbers, and this is not a math class. Nobody came here to do extra math. That's what algorithms is for. All right. So any other questions about the exam tomorrow?
Was that the analysis question on the exam?
No.
All right.
The analysis question, of course, will be a tree question. So any other questions? If there are no other questions, then class is dismissed. And I wish you all good luck on your exam tomorrow. I will remind you that the exam grades are typically higher on the second exam. This doesn't mean that you don't have to study, but it does mean that, like, relax. Take a deep breath.
Yeah, do you take demos?
I can do a couple demos today.
Okay.
All right. But otherwise, class is dismissed.
Thank
Thank
you.
you.
Yep, I will post the class recording. Okay, let me stop recording.